Acids and bases is our next unit. Super duper duper important because it is the connection between what we did last unit and what we're doing next unit. And what we're doing next unit is the penultimate topic. It's going to cover a large portion of the AP. It's also one of the more challenging topics. So this is your foundation, is super critical. A lot of this, what we're doing today, is review. But I'm going to point out some differences that are going to be occurring now and how we look at things a little bit differently in the second year course. First, though, you need to know different definitions of acids and bases. There's three primary acids and bases that you need to know: Arrhenius, BronstedLowry, and Lewis. Right now, we're just going to look at Arrhenius and BronstedLowry. So Arrhenius acids and bases, again, these are just different definitions. Some acids and bases fit into both definitions, some don't. Don't stress too much about it. But an Arrhenius acid is an acid that produces H+ in solution, okay? And an Arrhenius base is a base that produces OH- in solution. So they dissociate and they make these things. What we do need to know, where are my... Can't find my forward buttons because I'm too far over. This is not a good situation. Or, I guess if I hit, I'll have to do that. All right. So water then, as you know, is a liquid, but a small percentage of it actually dissociates into ions. So here I have some water. In this, I don't only have H2O, I have H+ and OH- floating around. And considering that we have more liquid than we do these ions, thinking about equilibrium, we know that our K is going to be super duper small. Because this is an equilibrium equation, we have a K that's associated with this. So if I were to ask you to write the K expression for this, what would you write? Correct. And each raised to the 1, right? So do I put it over water? No, because water is a pure liquid. This is our equilibrium expression for water. Because it's super important and it's the foundation of the pH scale and it is just critical, we've given it its own little subscript called W. So that's the KW. And the KW of water has a value of 1.0 times 10 to the negative 14th. That is super, super, duper, duper important because the entire pH scale is based off of that KW. All right? Another important thing about this KW expression, a lot of students forget it exists. And so if I ask a question, if I have an H+ concentration of so-and-so, what is the OH concentration? All you have to do is plug it into the KW and solve for the other one. Students end up doing crazy things like taking the H+, turning it to pH, making it POH, and then turning it into OH-, instead of just doing this. Okay, so you need to know that that is a usable expression, and I want you to know this by heart. Even though both this and that equation are on your AP sheet, you're going to be using it enough that it's going to be worth your time to memorize that equation. So what this led to was back in the early 1900s, there was a guy named Soren Sorensen. I feel sorry for him. I don't know why his parents would name him that. That's like Rui Ruissen. Philip Phillips. Exactly. Yes. I don't think Soren could sing, though. And he didn't look that cute, so he didn't have a lot going on. Anyway, moving on. Soren was a Danish beer maker. And so in his work, he got really basically tired of doing all the calcs with all the exponents because we know beer making, yeast, anaerobic metabolism, H+, all that stuff is very acidic and basic oriented. So he needed to have good data keeping on all of this. So he came up with the pH system. And what the pH is, and here's what I want you to think when you think P from here on out. P is the old-fashioned way of saying negative log of something. We dealt with tiny concentrations, so that's where the negative comes into play. This negative log is going to stretch in this class beyond just pH and pOH. You guys are going to learn about pKa's and pKb's, and P is always the negative log of stuff. All right? So if I want to find pH, I take the negative log of the H plus concentration in moles per liter. If I want to find pOH, I take the negative log of the OH concentration. And then, because of the connection here with, where did that 14 come from, do you think? 7 plus 7, but that didn't come first. What came first? The kW. Our kW was 1 times 10 to the negative 14th. If I take the negative log of that, what do I get? pH equals 14, right? So this is the basis of the whole, why is the pH scale to 14? It's because of the kW. All right? So neutral solutions have equal OH and H plus, so this would be 1 times 10 to the negative 7th, or 7 pH. This would be 1 times 10 to the negative 7th concentration, or 7 pH. 7 plus 7 is 14. So it's all going back to that kW. So here's our pH scale. Why we've chosen in this world to look at pHs instead of pOHs, pOH is just as legitimate of a scale. It's just a complementary scale. So 0 to 6.99 on the pOH scale is actually basic. It's flipped. This does have some limitations, the way you've learned it. You need to know that you can have negative pHs. pHs below 0 is pretty common, especially in this class. And you can have bases above 14 if they're super concentrated. So don't freak out if you're getting negative pHs or pHs above 14, because it will happen. All right, let's jump into some definitions. So for you to be able to do anything in this unit, write equations, determine pH, all that stuff, you need to be able to classify your acids or bases as strong or weak. And we're going to start with your acids. First off, what does it mean to be a strong acid versus a weak acid? Anybody remember? Naira? Exactly. If we have a strong acid, it's going to 100% dissociate into ions in solution. Done. 100%. So when you write a strong acid equation, you're going to have one arrow going in that direction, making all product. Weak acids, small percentages of them actually dissociate. So what kind of arrow do you think you use for those? Equilibrium arrows. Okay? So weak systems are equilibrium, strong systems have a single arrow going to the right. So let's go ahead and talk about strengths of acids. Who remembers some of the strong acids that we have? Anybody? HCl, yeah. Does anybody remember a rule for this at all? Okay, that's for ternary. Okay, we can do that. I kind of want to start with binary acids first. What are binary acids? That has H with one other element in it, right? So HCl, HF, H2S, H3P, all of those. Does anybody remember the 3 strong binary acids? Strong. Remember, I bring clay. I bring clay, those of you who had me. I know you did I bring clay for our new house for diatomics. All of you did that, right? Well, the 3 strong binary acids are just I bring clay. And end it. Any other binary acid is going to be strong. HF, H3P, H2S, H3N, those are all weak. All right, now we'll go to the ternary. JD, what did you say? Two or more O's than H's, it's going to be strong. And what do I mean by ternary? I mean acids that have polyatomics in them, acids that we name with the ick I ate a humongous bite thing. All right? So a good way to practice this would be to compare something like HNO2 to HNO3. Does HNO3 have at least 2 or more O's than H's? 2 or more O's? It has 2 O's versus, oh, sorry, HNO2. Does that have 2 or more O's than H's? No. So this is going to be a weak. HNO3 has 2 more, and it's 2 or more O's than H's, so this one is going to be strong. Now there's another set of acids that are always weak. Does anybody remember? It has carbon in it. So carbon-containing acids are weak. Does anybody know another name for carbon-containing acids? Organic acids. So all your cuckoo-cuckoo acids, the COOH, remember those, that functional group you learned in pre-AP? All those acids that have really long, that have tons of C's, H's, and O's that you don't know how to name, all of those. Those are considered to be weak. Any acid with a carbon in it is weak. So it's important that you know these rules. All right, let's go look at our next. We're talking about bases. And again, a strong base is actually something that dissociates 100%. So your strong bases are going to make some sort of ion, an OH minus. Can anyone remember what base, or I should say what hydroxides? The hydroxide ion is what makes basic things basic. So what hydroxides are 100% soluble, meaning strong? Group 1 and strontium and barium. These are our strong hydroxides. Any other hydroxide, any transition metal hydroxide, anything else, even like beryllium hydroxide, those are all going to be weak. Okay? There's also the consummate weak base called, what's that? Ammonia. Ammonia is a weak base. It's used all the time. You're going to know the KB of this thing by heart before the end of the year because we use it so much. That is very, very popular. And what this is kind of the basis of is nitrogenous bases. So I don't want you to freak out when you see these because they're not that hard. You can have something that's like CH3 2 NH, and that is considered to be a nitrogenous base. And what that is going around is nitrogen. Nitrogen has a lone pair, right? Then it's got 3 spots. If it's ammonia, these spots are all going to be just H's, right? But if we have any other base, we can replace these all with methyl groups if we need to. So we can put a CH3 here. With those 2, we could have 1 CH3. We can have 2 CH3s. All right? It doesn't really matter. And those are bases, and we'll talk about how to write equations with those soon. So don't freak out about them. Just know when you see any nitrogen thing with a bunch of stuff hanging off, it's probably going to be a nitrogenous base. And these groups, you can do an ethyl group, CH2, CH3. You can put any organic group, any alkene group off of this without a problem. And it won't get too complex, so in your AP problems, they don't go nutso on it. So all nitrogenous bases are weak, along with ammonia. So what we're going to do here, we're going to write the dissociation reaction. So the first step is to determine, and you're going to get sick of me asking you to classify these acids and bases as weak or strong. HF, what is that? Weak what? Weak acid. So it's going to dissociate, and it's going to be an equilibrium system because it's weak. It's not going to 100% dissociate. How much? Well, we'll get to that. We'll figure out percent dissociation when we get some numbers starting tomorrow. So here, what is that going to dissociate to? Now, a small amount's going to do it, not a lot of it, but it's going to do that. So based on that, is this an Arrhenius acid or base? We kind of already said what HF was. It's an Arrhenius acid because we're producing H plus in solution, based on its definition. All right, here's a crazy acid we don't know the name of, but do we care? No, because what is it? This is going to be weak. So equilibrium, what two ions are we going to dissociate partially into? O minus. All right, and is this an Arrhenius acid or base? Acid. All right. Barium hydroxide, weak or strong? Strong, so it's a single-headed arrow. And what are we going to make? It's totally going to bust up into its ions. Totally, bam. What is it going to make? 2OH minus. Now, weak stuff, there's weak bases, there's weak acids that will not just immediately bust up into ions. Stepwise stuff happens. But for strong, we're going to bust up into ions, and that's our equation. Is this an Arrhenius acid or base? Base, because we're producing OH in solution. Lithium hydroxide, strong or weak? Strong. What do we think? What ions? Plus OH minus. Strong, acid or base? Base. Uh-oh, water. It's aqueous, yes, correct. It's weak. Couple reasons. I never said that, but why is water weak? It doesn't fully dissociate, and how do we know that? We just kind of talked about something. No, not. Remember, we're talking about this in ions, so in neutral water we have the same number of H pluses as OH minuses. But what exists that makes us know water is weak? That KW, right? This is an equilibrium system. You have a K for it. So there's no way this could be strong. So this is going to dissociate into H plus and OH minus to a certain degree. Is this an acid or a base? Arrhenius. It's both. By definition, it's both. Does anybody remember what that's called? Something that has characteristics of both? I'll start to give you a hint. I want you to yell it out if you remember it. Amphimorphic? No, we are not doing rocks or lizards or whatever. Amphoteric. Amphoteric is a substance that can both accept a proton and donate, or can produce both types of ions in Arrhenius situations. All right, this one's important, even though it looks like it's super easy. And theoretically it is, but what do you notice about this acid that's a little different than any of the ones we did before? What, Jacob? It's what? It's not diatomic, you're close. It's diprotic. It's polyprotic. Polyprotic acids are special. Okay, this is a weak acid, right? So it's not just going to bust up into all its ions. It's weak. Polyprotic acids disassociate stepwise. It only loses one H at a time. And that's really important when we get to calculating pH for a couple reasons, which we'll get to. But this is weak because it's carbon containing, right? And it doesn't have two or more O's and H's. So we're going to only lose one H at a time, making H plus HCO3 minus 1. And then a second reaction is going to occur where we get HCO3 minus 1, and it's going to make H plus what? CO3 minus 2. This first equation is going to contribute to the pH primarily. The concentration of the first dissociation is mathematically way more significant than the concentration of the H plus on the second step. So when we eventually do calculations, we're only going to look at the first steps. And that does matter because instead of a 2-to-1 situation, we're always going to say it's just the first H that matters. That will make more sense when we start to do it. Just kind of put it in the back of your head right now. polyprotic acids dissociate stepwise. Okay? All right. Next, calculate the pH and pOH in each of the following aqueous solutions. Indicate whether the solution is acidic or basic. So, P, negative log of, right? So if we take the negative log of the H plus, that gives us pH. If we take the negative log of the OH minus, it gives us pOH. So we're going to have to find pH and pOH in both for every single one of these. We'll do that. We're only going to do these four. We're going to do them pretty quickly. But we got to talk about sig figs and pH. Sig figs and pH are different than sig figs for normal numbers. We know that this is how many sig figs in the normal world for concentration. 2 sig figs. That means we need a pH with 2 decimal places. The decimal places are what indicate significance in pH, not that first number. That first number has to do with the log, and I can never remember. I know there's like an abscissa and a mantissa in log rules or whatever, but I do remember back in my day, there were log tables in the back of my book. I didn't have to use a slide rule. I'm not that old, but I'm pretty old. And so we had log tables in the back of the books where to find the exact pH or exact log, we'd go to the column, and the column always represented the first number in the pH, like 1, 2, 3, or the first number in the log. And then as we went down the table, we got our decimal places. So this is what counted towards significance. That first number just has to do with like the exponent. So decimal places only. So what would be my pH? Negative log of 1.4 E negative 3. I need 2 decimal places. Let's go. 2.85. And how do I find pOH? Because I need that. 14 minus that, and that's going to be 11.15. All right. Let's go to the next one. Y'all can be calculating all these, so we get answers pretty quick. If I take the negative log of H plus of 7.11, first off, how many decimals do I need? 3 decimal places. So what's my pH? 10.148. Therefore, my pOH is no. 14 minus 10.148 is 3.852. Yeah, 3.852. 14 minus 10.14. Okay, all we're going to do are the next two. Now, if I take the negative log of the OH straight, what am I getting first? pOH. So how many decimal places in this one? 3. So what's my pOH? 6.682. Therefore, my pH is 7.318. And lastly, I want to do this one because it's going to be something that's going to be a little different. If I take the negative log of 4.0 to 2 decimal places, what is my pH? .6 what? I only need 2 decimals. Negative 0.60. It's negative. That's okay. pOH then is 14 point, and it's above 14, and that's okay. All right? So are we all good with going that direction? From the concentration to the pH, super simple. So now let's take a look going from pOH or from pH to the actual concentrations. So before we actually just jump in and start doing it, the keystroking here is super, super important, and it needs to be second nature to you guys. So let's figure out how we do that. If we have pH, it's equal to negative log of your H plus, right? So if I'm trying to figure out just the H plus concentration, I'm going to move my negative to the other side. So I get negative pH is equal to the log of H plus. How do I get rid of log? I do 10 to the right? So that gets rid of that. So pH, 10 to the negative pH is equal to the H plus concentration. And the same thing, 10 to the negative POH is equal to the POH concentration. So when you're entering this in your calculator, you're going to hit second log negative pH, and that's going to give you the number. Students tend to forget to make that pH negative, and that's important. So what would be the H plus concentration here? Okay, let's watch with sig figs. How many sig figs are in this pH? No, 2. So what would be my concentration to 2 sig figs? 3.9 times 10 to the negative 8. Now this is going to have some units on it. The pH didn't. Thanks. The pH didn't, but this does. What are the units? Moles per liter. Good. All right. pH is equal to a, oh wait, we got to find the OH concentration. What's the fast way to do it? Perfect. The KW, 1E negative 14 divided by this will give us the OH minus concentration. So I want you to use the KW when you're going between these two. 2.6 times 10 to the negative 7th moles per liter. Now this one, I don't want you to put it in your calculator. Stop. Put your calculator down. I've written enough AP multiple choice, and I've written some where you're expected to be able to deal with these nice clean pHs and logs straight up without a calculator because they're in the multiple choice. So if we have a nice clean no decimal number, what would the H plus of this be? 1 times 10 to the negative 11th. Okay? We know OH negative, it's that factor of negative 14, 1E negative 14, right? So what would this concentration be? 1 times 10 to the negative 3, because when we multiply exponents, we actually add them. Okay, so something like this, you need to get comfortable, even though on this particular test, I'm not taking your calculator away, you will eventually get problems like this where I will take your calculator away, but just keep it in mind. So practice that as much as you can. So this one, this will be our last one. POH, if I do 10 to the negative this, what am I ended up calculating? Concentration of OH minus. So to how many sig figs do I need? 3 sig figs. And what is my OH minus concentration? 589 moles per liter. So then what would my H plus concentration be? 1 times 10 to the negative 14th divided by 0.589. It's going to be really small. 1.70. Oh, times 10 to the negative 14th moles per liter. Okay? So y'all comfortable with how to get to and from pH and OH and H plus and OH minus. That's very much a Chem 1 skill, so that's why I'm kind of flying through it. Okay? All right, let's move on to the next definition. Won't take us too long, of the Bronsted-Lowry. Bronsted-Lowry, some people say Lowry-Bronsted, doesn't really matter, it's all the same. And what it is, it has to do with the transfer of a proton. Don't let that freak you out. If we have a hydrogen atom, we have 1 proton and 1 electron. When it becomes H plus, what happens? Electron's gone, leaving behind what? It's just a proton, right? So H plus is a proton, and that's why the terminology will be that way. So an acid, by definition, is a Lowry-Bronsted acid is a proton donor. It's going to give away an H from itself. A proton acceptor, then, is your Lowry-Bronsted base. So you guys need to be able to write equations where you add acids and bases to water, And whether this is wrong, it should be single-headed arrow. Whether or not it's strong or weak will indicate what kind of arrow. But you have to decide what's going to donate and what's going to receive. So we know HCl is hydrochloric acid. Obviously, it's going to be a proton donor. So it's going to donate its proton to water, making Cl minus. The acid, the HCl to the Cl minus, is called a conjugate acid-base pair. Conjugate acid-base pair. Conjugate acid-base pairs only differ by 1 H. That's how you know they're pairs. So sometimes they give you two things and say, are these conjugate acid-base pairs? If they differ more than just by 1 H or by some other random stuff, they're not. So this is my conjugate acid base. This is my base along with the conjugate acid. Just by definition, the conjugates are your products. So it makes sense. This is the acid, this is the conjugate base. If I were to reverse this reaction, the Cl would become the proton acceptor, and that's why it's considered a base on this side. Okay? All right. So what we're going to do now is, this is really not hard. This tends to confuse students, but you just be calm. For each of the following acids, write the formula for the conjugate base. If these are acids, what do they do? Donate H pluses. So we're going to make them donate an H plus, and when they donate an H plus, we're going to make the base. We're not asking for equations here or anything, but if H2PO4 minus donates an H, what do we make? Yes, HPO4 minus 2. Go down to B. What's B called? No hypo. Chlorus, right? ClO is hypochlorous. ClO2 is chlorus. ClO3 is chloric. And ClO4 is perchloric. All right, so this, if we donate, becomes ClO2 minus. Water, as an acid, will do what? What will it make? OH minus. Now, don't be afraid of these nitrogenous things here. This, I know I said they're always nitrogenous bases. Unless they accept something, this is a charged nitrogenous base, so it's capable. It's really an acid, right? And so it's going to give up, always give up H's on the tail here. Never mess with the H's that are in with the methyls, ethyls, whatever. So we're only going to donate one on the end. It's so easy. So what do we get? NH2, that's it. So you donate or add from the end of those things. This is kind of a trick. For each of the following acids, is that an acid? No, it's actually the strongest base ever. So this is not an acid. The reason I put this up here, I don't want you going, oh, that's going to make this. No, it's not. It is not. OH minus ain't donating. OH minus is going to accept, accept, accept. All right, NH4 plus, what's it going to do? Donate and make NH3. Okay? All right, so let's go do the next slide. For the following bases, write the formula of the conjugate acid. Since these are bases, what are these going to do? They're going to accept an H plus. So what is OH minus going to make? H2O. What is Cl minus going to make? HCl. Remember, polyprotic acids go stepwise, both directions. So this ultimately might make carbonic acid, but what is it going to do first? HCO3 minus. Water, when it accepts, will make H3O. We know about that H3O plus. This one, don't stress. Shove it on the back end. And what do we get? Yep. And the way this looks, again, that N is in the center. Sometimes if you know what it looks like, it's not as scary. This ethyl group is here, and then we got 3 H's coming off of it, and it's got a positive formal charge, because 5 minus 4 is plus 1. Okay? So that's what it looks like. Don't be afraid of it. And it's always these H's that we mess with, which are always here. And the last one, same kind of situation. what do? Just tag it on, NH+. Okay, so those are the basics. Today we're actually going to start the meat of what we're doing, and the meat of what we're doing has to do with, oh, we're not to the meat yet. Sorry, we have to do some Lowry-Bronsted acid writing. We're going to have to hurry, so let's move quickly. I'm actually going to do a lot of talking and not a lot of accepting information because we have to bust a move. So just take notes. HCl, we know that is a strong acid. I'm going to add it to water because the instructions say add the following to water. Since it's a strong acid, it's a single-headed arrow. This being the acid makes that the base. The acid then is the proton donor, so we're going to make Cl- plus H3O+. So Cl-, I will ask you, if HCl is the acid, what is Cl-? Conjugate base. What is H3O+? Conjugate acid. That's what you need to be able to do. So the next one, ammonia, let's classify that. It's a weak base. So because it's weak, we're going to have a double-headed arrow. And the double-headed arrow means the base, well, not the double-headed arrow, the base is weak, so it's going to accept the proton, making NH4 plus OH minus. This is what makes ammonia basic, right there. When it's in water, it makes OH minus. This doesn't fit the Arrhenius acid-base definition, but it fits the Lowry-Bronsted acid-base definition. So this is the base, this is the acid, this is the conjugate base, this is the conjugate acid. No. Bink, backwards. That one looks like that. This is the conjugate acid, this is the conjugate base. And I caught myself because I knew OH minus could never be an acid. So I saw that and went, nope, that's wrong. All right, HCN, classify it. Weak acid, carbon-containing acid. So we're going to have a double-headed arrow. We're going to donate a proton and make Cn- plus water accepting it, making H3O+. Water is the base. Cn- is the conjugate base. H3O+ is the conjugate acid. Okay. I'm not going to do these other two for time's sake. We all know that's a weak acid, right? Okay. And this one is a what? Weak base. Okay. We know that this is not going to act as an acid because it's not charged. Usually if it's charged, it won't donate if it's already positive. Okay. So that is a weak base. And we know just to tag it on the end, right, to make NH3+. All right. Okay, let's go on to now the important part of what we're doing. I can't see. And that's calculating pH. So over here on the side of the board, kind of giving you, we're going to add to this list. Our job by the end of the next unit is to find the pH of 5 different things. You're going to find the pH of strong acids and bases, weak acids and bases, salt solutions, buffers, and invaders. So where students really foul up is on the AP. They're given a problem and they're like, what do I do? Because they don't stop, take a moment, and classify where they're starting. If you, from the get, are capable of knowing what you're given, this part won't be that hard. So you're just going to get so sick of me saying, what is it? What is it? What is it? Because we need to know. So today we're just going to look at the first one, strong acids and bases. This is the easiest one. And at the end of the day, for a strong acid and base, all you have to do is take the negative log of the concentration of the acid or base, and that will give you the pH and the pOH. Why is that? Let's just take a look real quick. HCl is a strong acid, and it dissociates to those two things. Do we agree? Because it's strong, for every one of these, we get one of each of those. So if I have a 0.450 number of moles per liter of this, doesn't that mean I have 0.450 moles of this per liter? And doesn't it mean I have 0.450 moles of this per liter? Because of that, when I take the negative log of that concentration, I'm taking it because of this. I'm still taking the negative log of the H plus. But in the strong, I just know all of these are going to become H pluses, so I can just take the negative log of that. Are we good with that? All right. So if we take the negative log of 0.450, what do we get? 0.347 is 3 sig figs, and it was the pH because we took the negative log of, it's an acid we're taking the negative log of, so that's making the H plus in solution, right? All right, so the same thing is true for the strong bases. In the world of strong bases, KOH, we know, will dissociate 100% into the OH minus and the K plus. So our assumption is if this is the concentration of the KOH, it is also the concentration of the OH minus. So if I take the negative log of this, what am I actually calculating? POH. So the negative log of 0.710, it's going to be 3 decimal places in POH world. 851? Well, they're not asking for POH, though, so what do I have to do? Subtract from 14, and what do we get? No, I think you did it. This is 13.851. 0.149. All right, that's an important thing. Let's not let that mistake happen, okay? Our POH makes sense to be low, and our pH makes sense to be high because it's a strong base. It better be a high pH, right? All right, so that's what we're doing today. We're done. So make sure you can write your equations. Make sure you tell the difference between weak and strong, and make sure you can find the pH of strong acids and bases. So tonight's homework, as simple as it may seem, is crucial because of the importance for your foundation of this stuff. All right, that was a long lecture, 42 minutes.